All right, let's dive in and tackle one of those classic mechanics problems that, looks pretty intimidating on paper. We're going to break it down step by step until it becomes totally clear and, honestly, pretty simple. You ever look at a physics problem that has a few different stages? Something slides, then it flies through the air, and you just feel your brain kind of grind to a halt? Yeah, trust me, we've all been there. These problems can seem confusing, but the secret is to just treat them as a series of separate, much simpler problems. Okay, so here is our challenge for today. It's a classic, problem 1.136. It says, a small body A starts sliding from the height h down an inclined groove passing into a half circle of radius h over 2. Assuming the friction to be negligible, find the velocity of the body at the highest point of its trajectory after breaking off the groove. It sounds like a real mouthful, I know, but we're going to slice right through it. So what's rule number 1 in physics? Never ever panic and jump straight to the equations. Before we even think about a formula, let's just break down what the problem is telling us and really visualize what's going on. Think of this whole thing like a puzzle. Okay, so what pieces are we given? Well, we know it starts from rest up at some height h. We're told friction is negligible. That's a big one. And we know the shape of the track. And what's the puzzle we have to solve? We need to find the velocity at the very peak of its flight path, but, and this is key, after it leaves the track. That one little word, after, is probably the most important clue in the entire problem. Right, so let's break this journey into two totally separate parts. First up is phase 1, the descent. This is everything that happens while the body is still touching the track, from that starting point all the way to the very top of the half circle, where it's about to launch. The problem gives us this huge, blinking neon sign of a clue with this phrase, assuming the friction to be negligible. Seriously, whenever you see this in a problem that involves something changing height and changing speed, your brain should immediately go to one of the most powerful tools we have in mechanics. And that tool is, of course, the law of conservation of mechanical energy. All this really means is that if you don't have forces like friction stealing energy away from your system, then the total energy just stays the same. It just gets converted from potential energy, the energy of height, into kinetic energy, the energy of motion, and back again. Now here's a super common place where people get tripped up. To use conservation of energy, you have to decide where your zero height is. And here's the secret. It doesn't matter where you put it, as long as you're consistent. For this problem, the absolute easiest choice is to just call the ground level, the bottom of that half circle, our 0 point. Okay, let's put it into practice. This table lays it all out. At the very beginning, up at the top, the body is at height h. It starts from rest, right? So its kinetic energy is 0. All of its energy is potential energy, mgh. Now let's look at the end of this phase, the exact moment it breaks off the track. Well, it's at a height of h over 2, so it has some kinetic energy now, 1/2 mv squared, and it still has some potential energy, mg times h over 2. Since energy is conserved, the total at the start has to equal the total at the end. So we just set mgh equal to 1/2 mv squared plus mg times h over 2. We do a little bit of algebra, and notice the mass m just cancels right out, which is always nice, and we can solve for the velocity v. It turns out that the speed at the exact moment it leaves the track is the square root of g times h. Boom. That is a huge milestone. Phase 1 is done. And now we move into phase 2, taking flight. The second that body is no longer touching the groove, it's a completely different situation. It's a free flying object, and the rules of the game have totally changed. This comparison shows it all. When it was on the groove, there were two forces acting on it. Gravity pulling down, and the normal force from the track pushing up. But the instant it's in the air, poof, that normal force is gone. The only thing acting on it now is gravity. And that, my friends, is the definition of projectile motion. Okay, now here's a really important question, and you just have to visualize it. Think about the very top of a circle or a half circle. What direction is the tangent line pointing? At that precise instant of launch, which way is that velocity vector aimed? Exactly. It's shot out purely horizontally. The geometry of the track guarantees it. And what does that mean? It means at the very start of its flight, its initial vertical velocity is 0. This simple little fact is the key that unlocks the whole rest of the problem. This brings us right to the end, and honestly, the most satisfying part of the whole solution, finding the apex, the highest point. This is where we get that aha moment, that clever little insight that makes this problem just fall apart into something beautifully simple. So let's just quickly remember a fundamental rule of projectile motion. Since gravity only pulls straight down, It can only mess with the vertical part of the velocity. The horizontal part of the velocity, assuming we neglect air drag like we were told, it just stays perfectly constant the whole time.
So here it is, the big reveal. The problem asks for the velocity at the highest point of the trajectory. Well, what defines the highest point of any projectile's flight? It's that one split second where its vertical velocity becomes 0 before it starts coming back down. But wait a minute, we just figured out that our little body was launched with 0 vertical velocity to begin with. That means it was already at its highest point the very instant it left the track.
And with that one single insight, the whole problem is basically solved. We've done all the heavy lifting. Now we just have to put it all together and state the answer. So the question asked for the velocity at the highest point of the trajectory. We just had our aha moment and realized the highest point is the launch point. And we already calculated the velocity at the launch point way back in phase 1. So the final answer is simply v equals the square root of g times h. That's it. So we got the answer. But look, in physics, the final number is cool, but the method you use to get there is so much more important. Let's wrap up by making sure we add the strategies we used to your problem-solving toolkit. So let's just quickly recap the big lessons. First, chop up complex problems into smaller, manageable phases, just like we did. Second, always define your 0 point for energy and stick with it. Third, remember velocity is a vector. Its direction is everything. That horizontal launch was the whole key. Fourth, try to see the motion in your head before you ever write down an equation. And finally, always be on the lookout for a conservation law. It'll save you so much work. And I'll leave you with a little something to think about. How would our answer change if that track was a full circle and the body actually had to make it all the way around the loop before launching? What other things would you have to consider then? Think about the forces at the very top of that loop. It's a great little follow-up problem. Thanks for joining me.